Hello everyone, welcome to this lesson. So in this lesson, we're going to continue our discussion on numerical integration. And numerical integration, basically, if I have only the function and I'm not going to deal with any numerical integration techniques, can I still get the area under the curve? And the answer is yes. Like in the last lesson, we dealt with the function ln of x, and our integration limits were 2 and 4. And we used the first technique to get that approximation, and it was called the trapezoidal rule. And it stated that I'm going to approximate my area here using a first order polynomial. And we did a first order polynomial, and the area under that curve gave the shape of a trapezoid. And this is where the rule got its name. And the area of a trapezoid is very simple. It's basically a width times the average height. And we find that here in this example, we have this white space, and this is the area that I left out, or quote unquote the error. So to get rid of the error, we added more trapezoids to approximate the error, and we saw that it actually, in fact, reduced the error, right? And we said that the area under this curve is basically adding the trapezoids, and we saw that the pattern, this line in this point in between, is coming between those two. So we generated this general equation. Now we also went through another type of way to actually get more accurate answers. Here we use the first order polynomial. How about if we use the higher order polynomial, or a second order polynomial? And this is what we're going to deal in this lesson. So in this lesson, we're going to go through approximating the same function ln of x between the bounds 2 and 4. But in this case, we're going to do it using the Simpson's 1/3 rule. And I'm going to go through why it's called the 1/3 rule. We're going to develop a program, or not so much develop a program, but also we're going to adjust the trapezoidal program to be a Simpson's 1/3 rule. So we're going to go through kind of the differences between these two codes, and of course compare the performance of the Simpson's 1/3 rule to the trapezoidal rule. So the first thing here that I want to go through is that with trapezoidal, the first order polynomial is just a straight line, and you need 2 points to describe a straight line. But if you're going to go to a second order or a curve, you actually need 3 points to describe a curve. So in this technique, we need 3 points: f of x naught, f of x1, and f of x2. Okay, and we're going to describe this curve using a special type of polynomial called a Newton interpolating polynomial that is going to describe it in terms of the x0, x1, and x2 and their corresponding function value, and it's represented down here. Now, I'm not going to go through the derivation of this, it's not important, but if we integrate this line, in other words, get the area under its curve, we get this resulting very simple formula. Now, b minus a is just the width of this interval, and this is the kind of the average height when you're dealing with the second order polynomial. So this is kind of representation of an average height. It's defined in terms of f of x naught, f of x1, and f of x2. Okay, now I want to turn this function into this, and mainly because I want to indicate two things. I want to emphasize two things, is that with the trapezoidal rule, you have one trapezoid, one segment, right? So it's a 1-to-1 in terms of the trapezoids and segments. But one application of Simpson's, in other words, one curve, is corresponding to two segments. So one application of Simpson's, two segments. Okay, so that's one indication, which means the h for a single application Simpson's is b minus a divided by 2. So I'm going to take this h and I'm going to plug it over here. So it's going to be b minus a divided by 2 is going to be h. So I'm going to have a 3 remaining here. So it's going to be h divided by 3. And the reason I'm writing it this way, because I wanted you to see one application of Simpson's corresponds to two segments, as opposed to the trapezoid one segment, and also where the name Simpson's 1/3 rule came from. And this is because of the 1/3 factor that I have here. Okay, and much like with the trapezoidal, what if I want to make it more accurate? Well, if you want to make it more accurate, do multiple applications of the Simpsons, as you see on the right hand side. So this is two applications Simpsons. And if each application has two segments, so two applications, we have, say, 4 segments here. So in Simpsons, we go from 2 to 4 to 6 to 8 in terms of the increase in n with the increase in the applications, as opposed with the trapezoid, it just goes 1, 2, 3, 4, 5. Now, if you look at this, what is the area? It's basically the area of this first application and the area plus the area of the second application. And this is basically the equation that we're going to use. And here, this part here is for the first application, you can see it's defined in terms of f of x naught, f of x1, and f of x2. And the second application, f of x2, f of x3, f of x4. So we see the same pattern that there are two common, f of x2 is common to both applications. So that's why we're going to have a 2 here, right? And we can take h divided by 3 as a common factor. Now, there are two patterns that I want you to see that in terms of this 2, that's very similar to the trapezoidal. But also this 4 is going to correspond to the odd numbers. So f of x1, then this is going to be 4f of x3, then also going to be 4f of x5, and so on. So when I define this sum, is going to be 1, 3, 5 to n minus 1. But in terms of the 2, you're going to find that it actually corresponds to the even. F of x2, that's going to be multiplied by 2. And also, when we do another application, you're going to find we have a common f of x4. So this sum is going to be defined 2, 4, 6, 8, and so on. And it's going to end at n minus 2 here. So this is a generalized formula for a multiple application Simpsons, for however many Simpsons you want to apply. And this is, again, going to be very important when we're developing the code. So let's go ahead and actually develop the code. So let's go here, and I called the other one trapezoid. So let's actually copy this because it's actually very similar in terms of code. So we're still dealing with the same function, so this doesn't change. And we're going to deal with the same error, so this doesn't change. Still upper and lower limit. Now with the n, we saw that we start at n equal 2 and we go n 2, 4, 6, 8. So one thing that we will change is this initial n is 2, and also this one has to actually up by 2. Okay, so that's the first change that we're going to be making. So if you look at this equation, we need to define h, and h is defined much like we defined it with the trapezoid, and we need to define those two sums, right? So this sum is almost ready, right? So this is the sum for this one, and we saw that it actually goes from I2 to n minus 2, right? But not only that, you're gonna see that it ups by 2, right? 2, 4, 6, 8. So we're gonna have to use the keyword step, and we're gonna say step 2. And this remains the same, right? We still have the same 2f of xi, and we're still starting from a. So we have one more sum. So we have, let's copy this, and we paste. So let's actually redefine the sum. So we're gonna say sum, say 1, 1, 1, so it doesn't conflict with this sum. And for this one, it starts from 1 to n minus 1. So that's from 1 to n minus 1, and also goes through a step 2. So it goes from 1 to 3 to 5 to 7 and so on. And we also want to change this 2 to a 4. So now we defined h, we defined this sum, and we defined this sum, and these two functions we just call like we did with the trapezoidal. So let's actually change this integral. It's just going to be now h divided by 3, and this is f of a plus the sum, which is going to be the sum for this one, then plus the sum 1, which is the other one, and it's still f of b. I'm still calculating the t for in the same way. Now I want to change this because now I'm outputting in the 30 seconds. So I'm going to change this 27 to 31. I'm going to change this 31. But also there's one more thing that I need to change. I actually need to change this I plus 1, and this is going to sound a little bit weird. Because with the trapezoidal code, the loops here were upping by 1. I didn't use the step 2. It didn't conflict with this I. So I could use this I in this context and this I in this context. But because this is upping by 2, it's actually going to get in the way of this I. It's actually going to make it perform in a weird way. So what I'm going to do, I'm going to use something else. I'm going to say use II, for instance. So I'm going to use II here. So I'm going to say II plus I plus 1, and of course I have to change it here too, and I'm gonna have to change it here. That's it, only because we don't want this to conflict with the i's in these two loops. And actually, that's it. That is the difference between the trapezoidal code and the Simpson's one-third rule code. And again, to go through the slight differences is here n now starts at 2. We have to define the sums slightly differently. The sum that we defined in terms of the trapezoidal was from 1 to n minus 1, but in this case, it's going to be from 2 to n minus 2, but now also with a step 2, and we have this new sum here that we defined. So we have, that's another change. And of course, how we calculate the integral, that integral is defined slightly differently. And that's it. And here, since for every application of the Simpsons, we add 2 more segments, we have to up the n by 2. And again, this is a slight coding issue. Just use another variable instead of I, so it doesn't conflict with the i's of these two loops. So that's it in terms of the change. So let's actually change this to Simpson's 1/3, for instance. So let's go ahead and actually run the code. So if I run the code, so let's actually maybe say sum2. Maybe this is not working for some reason. So sum2, and say sum2, and say sum2. And I run the code. All right, perfect, it worked. So here I have, it actually took only one application of the Simpsons to reach below a 0.1% true error, and I have 2.15796 for my approximation. And if you remember with the trapezoidal, it actually took 7 different trapezoids to go below 0.1%. So this is at a 0.07, and this is at a 0.04. So even with 7 trapezoids, the Simpsons reached a lower error with only one application. So let's actually do one more thing. How about we actually try to get to 0.01? If I want 0.01, you see I have two application Simpsons. I have a true error of 0.0031. I have a approximation of 2.15881, and remember the actual value is 2.15888. So how about we go below 0.001? If I do that, it's going to require 3 applications of Simpsons, and I'm at 0.0005% true error, and I'm at 2.15887, and again the true one is 2.15888. That is quite impressive in terms of the techniques. We only knew the function value, and we have not used any integration techniques, and we got an approximation that is accurate to 0.0005%. That is, if you're going to compare it to the true, that is almost as good as the true value. So these techniques do get very, very, very accurate approximations, almost as good as the true values. Okay. So kind of to recap what we learned in this lesson, we introduced the second numerical integration technique, Simpson's 1/3 rule, and it uses a second order polynomial, and the second order polynomial or curve is defined in terms of 3 points. We used a Newton's interpolating polynomial to represent it, and by integrating this, we get this very simple formula down here. B minus A is the width, and now this is the representation of the average height. Okay, and we also explained that one application of Simpsons is equivalent to 2 segments. So we applied this equation here, and we got this generalized, or this improved formula that shows where the technique actually got its name, the 1/3, the factor here. And to make this more accurate, we applied the Simpsons multiple times, and we saw that we got this generalized formula. This is the point. This is the point that both techniques have in common, right? And this is the point that we have in the middle here. And we saw that this point is 4, corresponds to odd numbers, 1, 3, 5, 7, and so on. And this point here that the techniques have in common goes from 2 to 4 to 6, and so on. actually very, very simple. We saw with one application of Simpsons completely surpassed the performance of 7 applications of the trapezoidal rule. Okay, because we got a true of 0.04 and the trapezoidal got a 0.07. Okay, well, this marks the end of this lesson, and I'll see you in the next lesson.